Hello, we are Team Rhode Island National Science Foundation established program to stimulate competitive research, or RINSF EPSCoR for short, along with the Rhode Island Consortium for Coastal Ecology Assessment, Innovation, and Modeling. Our project is Drones and the Bay, a program for mapping water currents using drone footage. Our technical director is Dr. Baylor Fox Kemper, who works at Brown University, and our associate director, Dr. Stephen Licht, who works at the University of Rhode Island. Our team consists of Matthew Cicchini, an electrical engineering and German major, myself, Danny Cruz, an electrical engineer and Spanish minor, and finally Seth Wojcikowski, who is also an electrical engineer. The RINSF EPSCoR is a collaboration of engineers, scientists, designers, and communicators from 8 higher education institutions developing new approaches to assess, predict, and respond to the effects of climate change on coastal ecosystems. Working together with government, industry, and communities, the RICAIM views the state as a great setting for the study and research on our local bodies of water. Our team developed an accurate method to detect currents using a drone. The method is low cost when compared to using satellites, buoys, or sonar, and is much more convenient and precise than drifters. Using a short, still, downward-facing video taken with a drone, our team can find water surface currents in a matter of hours, giving researchers the opportunity to take precise measurements of powerful, sufficient velocity, consistent, and reliable waves for efficient use and placement of marine turbines, leading to green renewable energy that can become vital to coastal areas. Rhode Island being the ocean state makes it a perfect place for research. We are happy to announce we were able to achieve the anticipated best outcome, which was to obtain a complete MATLAB program that can measure wave velocity fields and create a velocity gradient map for each video taken with a drone. Instructions were created for the program so the project can easily be adapted by other users and include optimal weather conditions, ocean conditions, and a guide for drone flying to obtain the most accurate wave velocities. Installation instructions of the program are included as well. Finally, further steps were taken to do initial tests of the current fields throughout Narragansett Bay with the largest magnitudes. This will help Baylor in his goals for finding where to place hydroelectric turbines. We were able to debug initial issues when installing the code by fixing the pathing to the correct files involved with MATLAB. One of the main issues was the MATLAB utilization of media info. Due to a high amount of data recording and comparing involved with our project, we implemented a function that saves important values onto an Excel file and fine-tuned some sections of the code to better fit our approach on the project. We wanted this program usable by essentially anyone, so we have created a simplified guide to help users install, run, and utilize the program for their own research. Finally, we implemented features to help the user analyze videos with ease each run. An important result of our successful project is a cost-effective and faster method of recording and analyzing currents for any body of water than today's technology mentioned earlier. The ultimate goal of marine turbine placements will also lead to long-term benefits for the environment, especially in coastal cities that can best apply this method of renewable energy. Here we have displayed a flow diagram of how the program functions. There's a lot going on here, but it is simpler than it looks. Essentially, the drone footage is patched to the code within MATLAB, along with proper calibration files and selected video parameters for accurate measurements. The core of the program runs off these functions. The first one is the call to the file of the drone footage. To make things easier, MATLAB will ask you to select the video from your device and the user simply must choose it. The next function is the call to the calibration file that will be used and has the same input method as the video file. More info on what this file is will be discussed later. Looking at the side-by-side list, we have 2 more key features. They both are drone parameters used for calculations in the code. The difference is that the one on the left is for DJI drones and obtained automatically through its respective function. The other is for non-DJI drones and must be entered manually to be used by its respective function. When using either one, depending on the drone used, it is important to comment the function that is not needed out and uncomment the function that is needed. The respective functions can be seen along with the pictures of the parameters. Now let's look at what the results are of running the code and a quick comparison of changing video parameters. Looking at the top image on the left side, we see the first step in the code analyzation. The code creates a window dissection using a frame from the footage. In this image, there are 50 windows, which is the default for any video when the square size parameter is left blank. Each window analyzes wavelengths across X number of frames during the time length of the footage, which can be changed by the user within the code. Longer times equates to a longer process with more accurate results and vice versa. However, picking too long of a time frame costs more and is redundant at some point, and choosing too short of a time frame loses a lot of data. The bottom image is the result of the code and what we are looking for when mapping currents. We can now compare it to the right side, where the square size parameter is changed from a blank value to 15 and results in 32 windows. Similar to changing time length, more windows result in a longer process time and accurate data and vice versa, but has the same consequences. For research purposes, it is important to determine the best video parameters that are cost and time effective. Details on how to navigate this are included in the manual. I assisted in processing the footage we recorded due to the processing power of my computer, while also keeping an organized system of saving results and comparisons. These videos can take anywhere from 30 minutes to a couple hours to process, so avoiding potential crashes in MATLAB is imperative. Since I handled this component, I needed to also find the best parameters to use for each video we recorded in order to keep it cost-effective and provide accurate data. Understanding what each parameter does and its effect was a focus area. Team collaboration was also important when I needed to know the drone parameters and getting proper calibration files/settings. Otherwise, this can drastically impact results and lead to a lot of lost time and inaccurate current maps, which would lead to many consequences. Placing the marine turbines in optimal locations is the most important result of our project. I will now pass it off to Matthew Cicchini, who will discuss his contributions.
Thank you, Danny. So as mentioned before, the chart seen here shows the process of the MATLAB code. So a lot of our time was spent debugging and stress testing the code to ensure its optimal use. One of my key jobs during this was the documentation of the results from the various tests. We decided it was best to collect all of this data and information and put it into a user manual that highlights the many different things we were testing. From the differences in flying conditions, meaning weather conditions, the resolution of the video, height of the drone, etc., to all the small changes that can be made within the code, we wrote out completely what we found to be the optimal conditions and parameters for yielding the best results. User manual also includes a step-by-step installation guide for MATLAB itself, as well as the copter current program, along with all of its various programs and files needed to run. We also explained the pathing of each individual file to ensure the program runs smoothly. We provided a detailed process of how to calibrate the drone and showed the many different parameters that can be changed within the code to change the results. Finally, we included a detailed troubleshooting section with some of the different problems we encountered along the way. So as I just mentioned, there are many different parameters within the code that can change the outcome of the results. As Danny highlighted earlier, square size is one of these major parameters that can be changed. In doing so, along with the various other parameters seen here, it can greatly affect not only how your results look, but how long it will take to process. So for example, changing the square size to a much smaller one will decrease the number of boxes in the rectified video. In doing so, you may get a result seen in the top right box here. But if you change it to include more boxes, and let's say you change the DT parameter as well, which increases or decreases the time between each frame of the video, you will get a result that will look something like the bottom box here. So why not just run everything with the longest possible time, shortest time between frames, and the largest square size? That can be answered with the age-old slogan, time is money. By increasing everything, you will certainly increase the accuracy of the system, but it will take significantly longer. As the example seen on the right shows, changing the parameters, as I mentioned before, will take the program from around 25 minutes to process to just over an hour of processing time. This can be balanced out with a more high-powered computer with significantly more RAM, but unfortunately, we did not have access to such. So from our testing and the computers that we had, we found that leaving most of the parameters to their standard values, but changing the DT parameter to a shorter time, would take a 15-second video clip on average 35 to 45 minutes to process. And for our purposes, this worked out pretty well. I will now pass it on to Seth Wojcikowski to share his contributions.
This semester was the most successful semester for our project from my perspective. After getting our program up and running the previous semester, my ultimate goal for this semester was to find the optimal flying conditions for the drone, the optimal camera settings for the program, and optimal weather conditions which yielded the most accurate data. The purpose of this goal was to find the correct settings which give researchers the most accurate data in an easy-to-use platform. At first glance, this seemed to be a very easy goal to accomplish, but after obtaining 15 different test videos, which after analyzing all yielded contradicting results, I realized I was going to have to come up with a more scientific method to figure out the best way to obtain our data. For example, when we needed to find the minimum and maximum altitudes which could yield accurate results, I took 6 flights at altitudes incrementing from 10 meters high to 110 meters above the water. From this, I found that our results were the most accurate between about 20 meters and 100 meters. After we used the same methodology for camera lighting, cloud cover, and wind speed, I was able to confidently say that we can give researchers an easy way to use the program. A MATLAB script was also created to find the Laplacian for adjacent current gradient windows. This showed which frames are more accurate based on the degree to which the magnitude of the currents was changing for adjacent current vector windows, basically showing the error in adjacent current vectors. Optimal flying results from test flights that we took found that windy conditions gave more accurate data than calm flying days. Video captured in rivers was also found to be unreliable compared to video captured in deep oceans. These two confirmations were hypothesized during our first semester doing the project, but we were happy to confirm those predictions this semester. The two videos taken at the right of the screen seem to show that slightly brighter videos are more accurate than slightly darker videos. This contrasts two other videos that were taken a few moments before the two videos on the right of the screen, and those two videos show the exact opposite results. So these 4 videos that I'm talking about, along with 6 other videos, show that accuracy is unreliable in shallow water conditions, where the bottom of a lake or stream easily distorts the video. The most repeatable and accurate videos were taken about 100 feet into open ocean at altitudes of about 100 meters. So future goals for the project. Our future goals for the project include detecting the movement of hypoxia throughout Narragansett Bay. Progress towards this goal was taken last Thursday as video was taken at Save the Bay in Providence. Plans are in the works with Dr. Baylor to continue mapping a comprehensive map of Narragansett Bay this coming summer, and also into my job next year. So I'd like to thank Professor Baylor at Brown University, our main technical director, for helping out all year on the project and for helping me out this past summer. He was a great teacher and gave insightful and encouraging feedback on our project. Constructive criticism is always the best. Thank you also to Dr. Lick for allowing us to use his drone for flight testing a couple times during the school year. And thank you to Dr. Sunak for allowing me to continue my passion for my summer research and for allowing us to have a fun capstone project.